As many of us know, good architecture practice is vital for the success of our software systems. But our investment in architecture doesn't pay off when the implementation doesn't match the design. Hi, and welcome. In this session, I'm going to walk you through a new research project to automate design conformance checks during continuous integration. Carnegie Mellon University and the Software Engineering Institute were instrumental in developing the field of architecture. SEI staff in the Architecture Design, Analysis, and Automation Initiative continue to collaborate on research in a growing software architecture community. That community has created and evolved a body of knowledge that guides the design of a software system to meet its business and mission goals. This body of knowledge takes the form of fundamental design principles, all-encompassing reference architectures, and concepts in between, including design patterns. The degree to which a system meets its quality goals is dependent on these architectural decisions. However, architecture can only permit, not guarantee, any system quality. Non-conformance between the architecture and the implementation puts the system at risk in realizing its desired qualities. Here is a familiar scenario. We create a design which is extensible and composable. We do that because we have a plan for an initial baseline release and a later release that will exercise that extensibility and composability. This is at the heart of directives like MOSA, Modular Open Systems Approach, and emerging directions like the Defense Innovation Board's commandment for iterative capability delivery. Then we develop an implementation of the design, and the implementation satisfies the functional requirements, but the implementation really doesn't conform to the design. It's not extensible or composable. We don't see that in the baseline release. You can't test for that. Months or years pass, and we start work on the version 2 release. At this point, we discover that the implementation is different from the design we thought we acquired. This is a problem that nobody wants to talk about. What is a program manager going to say? The contractor didn't deliver, but we paid him anyway? We start reworking the implementation, and time passes. V2 scope has shifted from add to a working system to rip the system apart and make it work again, and we eventually deliver the V2 release. The impact is real. For example, we talked with one program that planned to be open and extensible, and then had to spend millions of dollars and delay a capability by years because the implementation turned out not to conform to the design. We've seen many examples of this in our architectural work. In a software factory or DevOps environment, the time from baseline to detection at V2 might be shorter, but the nonconformances are no less hard to correct, and this impacts agility and velocity. Our vision is to solve this problem by creating an automated design conformance checker and integrate it into the continuous integration workflow to report nonconformances in hours instead of the months or year that it takes to discover these problems today. Continuous integration offers visibility into the state of the software system and associated quality, allowing immediate engagement of stakeholders throughout the project lifecycle. Adding an automated design conformance checker makes use of the investment in architecture and impacts two kinds of stakeholders. Developers use the tool to detect nonconformances during continuous integration testing. Automation enables early detection and allows remediation before the violation gets baked in to the implementation. System acquirers can write contracts requiring developers to use the tool and report results, providing visibility that they don't have today. Detection of nonconformances during a design conformance review, in conjunction with acceptance testing, allows program managers to hold developers accountable. We're bounding our focus to MOSA properties. These are hard or impossible to test, and critical as the government moves to more iterative capability delivery. That said, the work has applicability to many properties. Here we see an overview diagram of the checker. Our project is building the green box. We're in the first year of a 3-year effort. We'll drill down in the next few slides to highlight what we aim to accomplish and what we've learned so far. The inputs our source code and the system's intended design, the prototype will automatically check that the implementation reflects the design. To achieve that objective, reported non-conformances have to be accurate and timely. Recommendations correctly identify the non-conformance and detect violations at the commit that introduces the issue. We do that so that developers can take immediate action and provide feedback to improve accuracy and significance of the checker. Creating an automated design conformance checker will advance the state of the practice. Concrete evidence allows stakeholders to act on the violations and achieve the MOSA vision that we talked about earlier. We have assembled an interdisciplinary team with skills in code analysis, architecture, machine learning, and continuous integration. The central research of this project is extracting design from code, using machine learning to recognize abstractions commonly used in software architecture. A recent survey on machine learning from code characterizes 3 waves of progress. Initial applications applied off-the-shelf machine learning tools with hand-extracted features, rather than being learned from representative code. These tend to be rule-based and tailored toward detailed design elements. This approach is limited by features used to represent code and doesn't scale. Subsequent applications made feature extraction part of the machine learning pipeline. With it is the challenge of how do we embed multiple views of code, such as compiler representations, static code analysis, and design information in the form of frameworks, into a compact vector for classification and still preserve the important information. People look to natural language processing for inspiration. We can think of code as words. We can learn from how relationships between words and paragraphs and documents model some local context, but it doesn't capture the unique opportunities from program semantics to understand long-range dependencies between elements of code so important for architecture design. Current applications promise new machine learning models informed by programming language semantics. Techniques claim to achieve semantic understanding of source code because they can, with modest accuracy, predict the name of a method from the source code it contains. These views of code are limited to those observable within isolated methods because the techniques use paths along a method's abstract syntax tree to make its predictions. We see the abstract syntax tree in the figure to the left, and its encoding as a triple linking the source node to a destination node through the context path. Paths linking parameters to computing outputs tend to be more informative in method name prediction. However, the representation does not capture the relationships between methods within a single class, nor the relationship between classes. So what constitutes a good feature set for architecture design? Representing the code as a more general graph of entities provides insight into structure and allows dependencies to be captured and searched efficiently without all the details of abstract syntax trees. Modeling context in the form of relations can improve prediction performance. Richer representations allow for features with deep semantics that convey global properties and provide traceability to a wider range or larger pieces of the codebase that may comprise a design construct. A common intermediate representation of object-oriented design provides core semantic information, and extensible representations allow data from different sources to be integrated. Let's return to the extract design from code portion of the conformance checker to see where machine learning is applicable. Source code seen at the left is input. We use code analysis to mechanically extract as much semantic knowledge of code structure and behavior as possible, unambiguously and automatically. Once we identify the design constructs in the code, we can traverse the graph and abstract relations among constructs to build design fragments that constitute the as-implemented design seen at the right as output. We're using a data transformation pipeline here as an example of a design fragment inspired by the FACE technical standard that follows the MOSA approach. It consists of design constructs such as filters that read input, transform data, write output, and pipes that connect filters and provide buffering and synchronization. Bridging the abstraction gap between code structure and design construct is a hard problem and represents one of our contributions to the state of the art. Our feature engineering work is what will make this possible. Let's walk through this process as we build a graph from the source code, predict the construct, and build the fragment for the as-implemented design and discuss the challenges and what we are learning. Any machine learning project depends on input data. We've identified initial data sets for our tasks. Static code analysis tools extract structural information from source code. We're working with C++ object-oriented code from open source repositories with plans to scale to industry-sized systems. We ingest a software repository and build a graph representation of the code structure. The graph schema shown on the left illustrates the kinds of entities and relations we represent. Here we see a UML diagram for a graphics package designed using the composite pattern and a snippet of code for printing primitive shapes such as ellipse individually or in some combination. The code graph built from this source code captures the basic structural elements such as classes and methods and how they are related through inheritance and method call. We used these basic entity relationships as features in an exploratory project last year and found they provided some insights into the design constructs we were looking for. But we can extract a much richer feature set to improve on the results. C++ doesn't distinguish classes that act as interfaces, but clues in the code, such as the degree of accessibility, the number of public methods, and virtuality, the virtual methods without an implementation, provide evidence that graphic is an interface. Inheritance in C++ doesn't distinguish between type extension and implementation of an interface, but knowing graphic is an interface and ellipse and composite graphic provide implementations of the virtual methods that they inherit provides evidence that the relationship is interface implementation. An association relation, such as composite graphic using the graphic type in a container of leaf types, provides evidence of a composition relationship. An invoker-invokee relation, such as composite graphic delegating the printing to its leaf siblings, provides further evidence of a composition relationship. Feature engineering incorporates these different source code representations, providing multiple input signals for learning to detect design constructs based on textual, behavioral, and structural semantics. We are applying research in neural networks to encode the graph-based features in a meaningful way for classification. Once we identified the design constructs in the code, we can traverse the graph and lift lower-level relations in code to abstract relations among constructs to build a design fragment that constitutes the as-implemented design. These design fragments, represented as graphs, enable an automatic detection of conformance. The graph of the extracted design is checked for agreement with the intended design to locate inconsistencies. Here we see the as-implemented design is in agreement with the intended design as an instance of the pipe filter pattern that forms a data transformation pipeline consisting of 3 filters. Detection is augmented with checks against relevant canonical design knowledge. The design properties of the pipe filter pattern allow the overall computation to be treated as the functional composition of the computations of the filters, allowing the architect to reason about the end-to-end behavior as a composition of the behavior of the parts. Adherence to the pattern improves reuse due to the independence of the filters. Here we see violations of the design properties and constraints puts these desired qualities at risk. Where does the intended design come from? It could be a design pattern, like pipe filter, that satisfies the face reference architecture. It could be part of a framework put in place, for example, Spring Model View Controller or Qt Publish Subscribe. Or it could be from a modularity initiative to support key properties for proper use of common infrastructure, such as communication via interfaces and respecting service boundaries. Detecting non-conformances produces greatest value when issues are exposed close to the time of injection. Integrating with a CI tool such as Jenkins can complement existing checks for reliability and security by adding checks for extensibility and composability that together help ensure the software is more resilient. Continuous integration will enable an empirical evaluation in how we address the gaps in the state-of-the-art and barriers to adoption. We will use developer feedback to improve results. Getting feedback on correctness improves design extraction by providing new labeled data, and seeing how the developers treat the significance of the results improves adaptive filtering by capturing context-specific rules and exceptions to the design, since violations in one context may not be significant on another project. This year, we've been building out infrastructure that consists of graph representation, feature engineering, design knowledge, and conformance checking. We're assembling open source data and conducting initial analyses. Next year, we'll broaden the palette by adding more design knowledge and conformance checks and implementing adaptive filtering. In the year that follows, we'll fine-tune conformance checking, validate the prototype with experienced developers, and be ready to pilot conformance checking for C++ software. Software is constantly changing over its lifetime, as illustrated by the red line, due to fixing bugs and vulnerabilities, updating technology, and staff changes. What we want software to do also changes, as illustrated by the blue line, as requirements in the environment change and the design evolves to meet those needs. Over time, gaps between the software and the design emerge and grow. The goal of the Automated Design Conformance project is to keep software aligned with needs. When the gap has grown too large, the refactoring assistant being developed by the Entangling the Knot project will bring projects back into alignment. Looking further out into the future, you can read about our vision, where developers sketch proposed changes in the language of design, and trust that automation can realize those changes in a recent publication on next-generation automated software evolution.
Good afternoon, everyone. I'm Hasan Yasar. I'm a technical director at SEI and managing continuous deployment capability growth under SEI. So today I have Rod Nord and also Laurie Flynn, and which they presented a couple of minutes ago about their presentation, their research proposal, their research progress so far. So before really starting, I would like to have both of you, and Dr. Laurie and Dr. Rod, could you introduce yourself and what is your research area? I knew we presented your research and in an hour ago, so I would like to start from you, Dr. Laurie. So could you introduce yourself and what is your research areas?
Hi, I'm Laurie Flynn. I'm a senior software security researcher at SEI, and my focus for research for quite a while has been on improving various aspects of static analysis, and for the last 5 years it's been focused on machine learning use in static analysis mostly.
And Rod, could you introduce yourself?
Yes, hello everyone. I'm Rod Nord. I'm a principal researcher at the SEI, and I'm a member of the Architecture, Design, Analysis, and Automation Initiative. When I first got started, I got involved in developing practices for analyzing and designing software architecture that many of you may be familiar with. These are the quality attribute workshop for eliciting architectural significant requirements, attribute-driven design, and the architecture trade-off analysis method. But I've been interested in how do we use these practices in the software development lifecycle? So how can these better support Agile at scale and DevOps? And what happens when we don't use these practices and technical debt accrues? But as we all know, architecture can only permit but not guarantee important system qualities. So that led me to this current research project on developing automated checks to ensure code conforms to design.
Actually, both of the project I'm really interested as well. And while working for DevOps space, I see a lot of issues, either not doing the proper static analysis in the continuous fashion of everything right now we have been talking, and also the same thing for architectures. So I'm getting all the question from the chat room, which is great. There is a great interest. And Donna was asking, and how well does the automated design conformance translate to other languages other than C++? Rod, probably can answer that questions.
Yes. So we are focusing on object-oriented languages, initially to make this problem tractable. Last year we had an investigatory project where we were using, the Java language. But this year, we decided to focus on C++, but the front end uses static analysis tools to take the C++ language and build a graph representation from which we conduct the additional analysis in terms of feature engineering and conformance checking. So we're sharing infrastructure with another project that was briefed, the Untangling the Knot project that's using C#. So we're focusing on C++, but we're hopeful that there are enough common representations with C# and Java that we're keeping in mind that we could begin to support some of these other languages over time. Of course, there's some significant differences in how C++ deals with some abstractions, but that's part of the research where we'll see does the generalization provide enough signal to check for conformance, or do we need to what extent do these language specific properties also need to be taken into account?
Right. I would like to add another thought as well, what you said, the language. I think we can use the same framework throughout the continuous integration environment as well, right? Like building the framework that we're looking for, the code that has been developed from developers, and then maybe changing language later on, but eventually the same framework will be used multiple languages as well. Just learning basis will change, correct, right?
Yeah, that's our goal. Like a lot of other tools kind of use a front end to parse the different languages. We have that in mind as well.
Mm-hmm. Great. And I'm going to go to the next question I was asking from chat window. What metrics does SCAFE look for in code to determine security issues? And Lori, probably you'll answer that question.
Okay, sure. Yeah. So some metrics include code cohesion, lines of code in a function, in a file, in a class, in a program, significant lines of code. Also, we count the number of static analysis alerts per function and per file, and those metrics are also useful. We use tools. A couple of the tools that we use are Lizard and the CCSM tool, which works with a front end for Clang. And they both provide a lot of different code metrics that we use.
So since we are working the two projects, and I see a lot of similarities, because one is looking for architecture perspective, the other one is a security perspective. Both are using the continuous delivery, continuous integration environment. So when we look at that perspective, and could the two research prototype system can be combined in a way that we can improve the AI for each systems? So I will give you a time for each of you. So how can we combine both and secure the pieces and also the architecture conformance? Maybe I'll start from Lori, from you. What do you think about that?
So Rod and I have discussed this idea a little bit, and we're interested in that. We have some ideas about how that might be done in a simpler way, with kind of the separate systems just providing each other the results, and then using the results from one system as features for the classification for the other. We might also be able to reduce some duplication in both systems. If we're both using a particular tool, in fact, there's one proprietary tool that I won't name here, but that both of our tools are integrated with, that there could be efficiencies. Only one of them could use the tool in a pipelined environment. Ron, you could add more.
Yes, certainly. Yeah. So we've kind of discussed. There's like two aspects. One is the kind of the business aspect, or the capability that it's exposed to the user or to the developer. And, Hasan, you mentioned like DevSecOps. There's also been kind of the word thrown around DevResOps in terms of how do we make this system overall more resilient. And certainly, existing tools kind of target the reliability aspects in terms of finding traditional bugs, earlier. And then some of the work is moving towards security vulnerabilities. And then this capability adds kind of detecting design flaws to make the system more maintainable and sustainable. So part of that is kind of adding more to the repertoire of what defects can be found in terms of these three areas to overall make the software more resilient. And then as Lori mentioned, I think there's opportunities for sharing infrastructure. She's kind of pioneered the way, and we're in our first year of this project. So the first year we've been tackling both research challenges as well as building out some of the infrastructure. And so this first year, building end-to-end capability to check conformance for some candidate non-conformance targets. But as we move into year two, we want to be able to embed this more fully into a continuous integration environment. Learn from what Lori's team has found, and how do we start to bring in more feedback from the developer. So kind of a continuous integration, both giving feedback to the developer, but then taking feedback from the developer to improve the techniques as well.
So actually, it's a good point you brought up, right? It's a kind of DevSecOps is passion for me. And when we look at that perspective, yes, security should be part of architecture as well. I'm assuming, so if we have an architecture analysis in a secure way that we have done in our design, so what do you think about the confirming security design as well as part of the code that we are writing? So how the developer is addressing some security consideration architectures, and then how architectures we design at the beginning, so that use the conformance piece. At the same time, look for the SCAFEs that the rapid education research, see how can we collect the both and verify in a good perspective. So the question for you, right, like what do you think about and looking for a security analysis perspective in the code levels? I'm sure you're not looking for conformance only for validating architecture. You're looking for other quality attributes, right, in your code?
Yes, absolutely. So, it's a two-stage process. So as you mentioned, we want to understand what are the important quality attributes that lead to the design of an architecture that's going to fulfill those properties, and then use that architecture as a blueprint to create the implementation and to check for conformance. So, since, as I mentioned, we're in our first year, we've been focusing on design constructs that have to do more with maintenance, sustainability aspects as our initial focus. But we are interested in the technique will be general to look at other qualities, so security, certainly. Or other qualities that are important from a DevOps perspective, availability and performance, and bringing an architecture perspective could complement some of the existing security checks that tend to be more localized. And from an architecture perspective, we can start to kind of look at the code from a global perspective. What are the global aspects of the code that can support those important qualities as well.
And so then, Lori, I'll get back to you. So when we have a SCAFEs that we are using in our continuous integration environment, and we're expecting to have a plugin to be part of our build server as a Jenkins or as an example. So that plugin will get the multiple result of the static analysis tools. So I'm dreaming about that type of alert will be a good feedback to the architecture, right? Because we are looking for what type of alert and how the alert is related to the code perspective. What do you think about that, tying the alert to the architectures?
I think it would be very interesting to use information about potential architectural issues to use that for helping us to classify whether an alert or meta alert, whether a code flaw really is there. That's whether a code flaw a static analysis tool warns about really is there or not. So some, machine learning might find that, with some results from Rod's architectural analysis, that the flaw would be more likely to be true or false. And I think that there's great potential for that data to be helpful. And certainly during CI and during continuous integration development, I think, during a particular build, it's very useful. It would be very useful for a developer, both to find out if there are potential flaws determined by static analysis, and if potentially some of the architectural requirements, there might have been a regression. Some requirement might just be broken. So I think that it's very exciting, the idea of having a system that would detect both of those during CI.
So I'm looking for another thoughts in terms of the analysis in both. One of the biggest issues in the DevOps perspective, not actually issues, maybe the feedback or the advantage of the DevOps is getting a continuous feedback, right? So if we understand from our security perspective, architecture, feedback goes to the not developers, it goes to the architect as well, which is the pipeline is given that capabilities. So what do you think about getting a feedback, and what level of feedback this two research proposal will generate to the stakeholders, like feedback from SCAFE? So what the developer will learn from the systems, what they can do with respect to the adjudication perspective, like CI is generating something, what that information will be valuable for developer and other people. What do you think, Laurie? Like feedback, maybe recommendation, feedback maybe to this one or the skip others, or feedback is trust these resources. Any idea for what the feedback will be?
Let's see if I understand correctly. I think the feedback would it would be whether or not there are code flaws in the current in the current code that should be fixed, that are true code flaws that should be fixed. Is that what you were asking?
Exactly. That's the kind of important, because when I talk anytime with the developers, when they see the static analysis result, they don't know first of all, they know it's relevant or not. Second, they don't know how to fix it. They don't know how much time they will spend to fix that important one. Is it important or not? Or how much they can trust, because they may have many static analysis report is generated from the pipeline. So which one they will trust and what they have to do, which is one of the feedback mechanisms. I'm assuming this project will give them a concrete feedback what needs to be done. Here is the next step as an example.
So in the current project, the kind of what's to be done recommendation is, these flaws are the most important to fix right now, based on the confidence from the classifier, confidence that it's true. But we also have developed this prioritization scheme using a mathematical formula that the developer can insert that uses more than just the confidence. It can use some cost estimations that they develop. I think that's a really interesting additional area of research that I haven't done in terms of how do you make a cost analysis. That's a whole additional complementary area of research.
And Rod, anything you want to add for the feedback mechanisms, and what would be the report from architecture conformance perspective?
Yeah, we've been thinking about feedback from different perspectives. You mentioned like developer versus the architect. So certainly we would give immediate feedback to the developer to see if that there is a non-conformance. So we want to check to make sure it's correct, but also significant or relevant, as you mentioned. So we want to see what the developer actually does with the result. Do they make the fix? Do they say it's correct and it's worth making? Maybe they say it's correct, but they don't make the fix. So people talk about kind of an effective false positive, even if it's true and they don't, it's not useful. That gives us some feedback. There could be some cases where that maybe the design needs to be changed. So that goes to the architect. Maybe there is an issue with the design. Certainly in a DevOps environment, the design is evolving as well. It needs to be looked at. Or there could be some project-specific exceptions. So maybe a particular layered pattern is required, but for certain cases, like for performance, there might be a project-specific exemption. And we want to understand that. The other aspect you mentioned is, so this would give, what our goal is to give enough concrete, evidence, so that developers can make the fix. So not necessarily, say what the fix is, but show the evidence in where this occurs. So I think like one of the challenge with machine learning, some techniques are more of a black box. So that's something that we're looking into is how do we, carry forth this evidence along the analysis chain so that we can present enough context to the developer so that it is useful and it is used and acted on.
Great. So I'm looking for the questions, and I saw there is one question from audience. And Donna was asking, can Scaffold perform a differential analysis and for just patch to be used on existing software, or is it best only for use during software development?
Let's see. To be used on Scaffold can be used on existing software. In fact, we're in the middle of integrating it with CI systems, so it isn't yet able to be used during continuous integration. We're adding all kinds of features to do that. And we have added many features to do that. So right now, it is indeed useful in that way as a one-shot order things. But soon it will be able to be used both ways.
I guess it's a matter of the time, matter of learning, right, from the system. Once we build up the overall system, can be used and during the software development environment as well. So it was a great discussion. I wish we had more time to talk, both of you. And I love this topic. And I'm sure a lot of participants as well, they would like to enjoy to see how can we automation board perspective and use that. I would like to thank you, each of you, for your participation and also the great presentation you presented. And looking for you to have the next sessions, maybe next year. Thank you.